Section 1.8, Logarithm Functions. In this section, we'll take a look at a function that is related to the exponential functions we looked at in the last section. We will look at logarithms in this section. Logarithms are one of the functions that students fear the most. The main reason for this seems to be that they simply have never really had to work with them. Once they start working with them, students come to realize that they aren't as bad as they first thought. We'll start with b is greater than 0, b is not equal to 1, just as we did in the last section. Then we have y, which is equal to log of base bx, is equivalent to x, which is equal to b to the power of y. The first is called a logarithmic form, and the second is called the exponential form. Remembering this equivalence is the key to evaluating logarithms. The number b is called the base. Let's do some quick evaluations. So without a calculator, we're going to give the exact value of each of the following logarithms. So we have the log of base 2 of 16. So to quickly evaluate logarithms, the easiest thing to do is to convert the logarithm to exponential form. So let's take a look at the first one, the log of base 2 of 16. So first, let's convert to the exponential form. The log of base 2 of 16 is equal to what? It is equivalent to 2 has an exponent of what for where it's equal to 16. So we're really asking 2 raised to what gives 16. Since 2 raised to 4 is 16, then we get the log of base 2 of 16 is equal to 4 because 2 to the 4th power is equal to 16. Well, we'll not do this remaining parts in quite this detail, but they were all worked well in this way. The log of base 4 of 16. The log of base 4 of 16 is equal to 2 because 4 squared is equal to 16. Note the difference between the first and the second logarithm. The base is important. It can completely change the answer. Part C. The log of base 5 of 625 is equal to 4 because 5 has an exponent of 4 for it to equal 625. So basically what you're asking yourself is, what is the exponent on base 5 to get 625? Well, the answer is 4. So in this question here, it says, what is the exponent on base 9 to get 1 over 531,441? Well, recall that this is 1 over 9 to the 6th power, which means 1 over 9 to the 6 is the same thing as 9 to the negative 6th power. And negative 9 to the 6th power is equal to 1 over 9 to the 6th, which is equal to 1 over 531,441. So therefore, the exponent has to be negative 6. Now, the log of base 1 over 6 of 36 is equal to what? So what is the exponent on 1/6 to get 36? That's your question. Well, 1/6 raised to the negative 2, if we take the reciprocal, it becomes 6 and makes this exponent positive. 6 squared gives us 36. So 1/2 raised to what power, 1 over 6 raised to what power is going to give you positive 36? Well, the answer is negative 2. Now the log of base 3 over 2 of 27 over 8 is equal to 3. So again, we're asking ourselves, what is the exponent on the base 3 over 2 to get 27 over 8? Well, 3 over 2 raised to the 3rd power gives us 27 over 8. So the answer is 3. Now, there are a couple of special logarithms that arise in many places. These are the following. The natural log of x, which is equal to the log of base ex. This is called the natural logarithm. The log of x, which is equal to the log of base 10 of x. This is called the common logarithm. Now, in the natural logarithm, the base e is the same number as the natural exponential logarithm that we saw in the last section. So here's a sketch of both of these logarithms. So in red, we have the natural log of x, and then in blue, we have the common logarithm of x. So remember that the base for the natural log is e, the base for the common logarithm is 10. So from this graph, we can get a couple of very nice properties about the natural logarithm that we will use many times in this and later calculus courses. Now, as the natural log of x, as that function approaches positive infinity, well, so does the x-axis. The x values are also approaching positive infinity. Now, if the natural log is approaching negative infinity, as you can see here, as x is approaching 0. So as x is going towards 0, this function is going towards negative infinity. Now, let's take a look at a couple of more logarithm evaluations, some of which deal with the natural or common logarithms, and some of which don't. So for example 2, without a calculator, we want to give the exact value of each of the following logarithms. So for the first one, we have the natural log of the cube root of e. Well, it's equal to 1/3, because rewriting the cube root of e is e to the 1/3, which is equal to 3 the cube root of e, because the base is e. Now, what is the base for the common logarithm? The base for the common logarithm is 10, and 1,000 can be written as 10 to the 3rd power, so therefore the answer is 3, because 10 to the 3rd power is equal to 1,000. The log of base 16 to get 16, well, that means 16 has to have a power of 1 to get 16, so the exponent is 1. And what does the exponent have to be on 23 to get 1? Well, 23 to the 0 power is going to give you 1, so therefore the answer is 0. And then in part E, what is the exponent on base 2 to get the 7th root of 32? Well, recall that the 7th root of 32 is 32 to the 1/7. And if we rewrite 32, rewriting 32 as 2 to the 5th power raised to the 1/7, well, 5 times 1/7 is 2 to the 5/7. So we figured out that the exponent on base 2 to get the 7th root of 32 is equal to 5/7. Now, this last set of examples leads us to some of the basic properties of logarithms. 1, the domain of the logarithm function is 0 to infinity. In other words, we can only plug positive numbers into a logarithm. We can't plug in 0 or a negative number. The range of a logarithm function is negative infinity to positive infinity. The log of base b to get b is equal to 1, meaning what is the exponent on base b to get b? The answer is 1. The log of base b of 1 is equal to 0. Again, what is the exponent on base b to get 1? Well, the answer is 0. The log of base b of to get b to the x is equal to x. So what is the exponent on base b to get b to the x? Well, the answer is x. And over here, if you have b raised to the power of the log of base bx, then your result is x. Now, the last two properties will be especially useful in the next section. Notice as well that these last two properties tell us that f of x is equal to b to the x, and g of x is equal to the log of base bx, are inverses of each other. So here are more properties that are useful in the manipulation of logarithms. Number 7, the log of base b of xy is equal to the log of base bx plus the log of base by. So the multiplication of the logarithm here, a single logarithm, turns into addition. The log of base b of x divided by y, this division turns into subtraction, so the log of base bx minus the log of base by. And then the last one, 9, the log of base bx to the power of r. This is the property of logarithms rule. So now this becomes r, meaning the exponent times the log of base bx. Now note that there is no equivalent property to the first two for sums and differences. In other words, the log of base b of x plus y does not equal the log of base b of x plus the log base b of y. Remember, it has to be multiplication to get that property. And the log of base b of x minus y does not equal the log of base bx minus the log of base by. Now, example 3. We're going to write each of the following in terms of simpler logarithms. So for part A, we have the log of x cubed y to the 4th z to the 5th. Now, what the instructions really mean here is to use as many of the properties of logarithms as we can to simplify things down as much as we can. So the log of x cubed y to the 4th z to the 5th property 7 above can be extended to products of more than two functions. And once we use property 7, then we can then use property 9. So we're going to separate these logarithms because this is multiplication into addition. So this is the natural log of x cubed plus the natural log of y to the fourth plus the natural log of z to the fifth. And then using property 9, now this becomes 3 times the natural log of x plus 4 times the natural log of y plus 5 times the natural log of z. In part B, we have the log of base 3 of 9x to the fourth divided by the square root of y. So when using property 8 above, make sure that the logarithm that you subtract is the one that contains the denominator as its argument. Also note that we'll be converting the root to fractional exponents in the first step. So since we have division, we have to separate this by division. So we have the natural log of base 3 of 9x to the fourth minus the log of base 3 of y to the 1/2. Now over here we still have a multiplication between a number and a variable, so we need to separate that using property 7. So we have the log of base 3 of 9 plus the log of base 3 of x to the fourth minus the log of base 3 of y to the 1/2. And now what we need to do is then simplify. Well, what is the exponent on base 3 to get 9? Well, the answer is 2. So this now simplifies to the number 2. And then we're going to use the property 9 to rewrite the exponent in front. So this is plus 4 times the natural log of the common logarithm of base 3 of x. And then writing the exponent here, which is minus 1/2 the log of base 3 of y. And then part C, the log of x squared plus y squared over x minus y to the third power. The point of this problem is mostly the correct use of property 9 above. So the first thing we need to do is, since this is division, we need to subtract. So we get the log of x squared plus y squared minus the log of x minus y to the third power. Well, this first term, there's nothing else for us to simplify. In the second term, we need to bring the exponent in the front, which becomes minus 3 times the log of x minus y. So you can use property 9 on the second term because the whole term was raised to the 3. But in the first logarithm, only the individual terms were squared and not the term as a whole, so the 2's must stay where they are. Now the last topic that we need to look at in this section is the change of base formula for logarithms. The change of base formula is the following. The log of base bx is equal to the log of base ax over the log of base ab. This is the most general change of base formula and will convert from base b to base a. However, the usual reason for using the change of base formula is to compute the value of a logarithm that is in a base that you can't easily deal with. Using the change of base formula means that you can write the logarithm in terms of a logarithm that you can deal with. The two most common change of base formulas are the following. The log of base b of x is equal to the natural log of x over the natural log of b, and the log of base b of x is equal to the log of x over the log of b. So in the first one, we're using the e as the base, and over here we're using the 10 as the common logarithm base. So in fact, often you will see one or the other listed as the change of base formula. In the first part of this section, we computed the value of a few logarithms, but we could do these without the change of base formula because all the arguments could be written in terms of the base to a power. So now, for instance, the log of base 7 of 49 is equal to 2. So what is the exponent on base 7 to get 49? Well, that's 7 squared, which is equal to 49. However, this only works because 49 can be written as a power of 7. We would need the change of the base formula to compute log of base 7, 50. So we don't have a number that we can raise 7 to get 50, so this is why we have to use the change of base formula. So it becomes the natural log of 50 divided by the natural log of 7, which gives you the following numbers, and therefore it's equal to 2.010382137. Or, instead of using the natural log, we can write this as the common log of 50 over the common log of 7. So what that allows us to do is that allows us to be able to use the calculator. So let's go ahead and do that here. So what we want to do is we're going to write the natural log. So we're going to find the natural log of 50. And then we're going to divide that by the natural log of 7. Because this is a base of e on our calculator, then that gives us the result here. And if we want to use the common logarithm, we can get the same answer. So if we use the log of 50 and then divide by the log of 7, then that gives us the same result. But you have to make sure you use the log and the log, the natural log and the natural log. You can't use the log and then the natural log in the denominator here. So it doesn't matter which we use. We will get the same answer regardless of the logarithm that we use in the change of base formula. Note as well that we could use the change of base formula on a log of base 7 of 49 if we wanted to as well, because the natural log of 49 divided by the natural log of 7 is going to give us 2. So this is a lot of work, however, and this is probably not the best way to deal with this. So in this section, we saw how logarithms work and took a look at some of the properties of logarithms. We will run into logarithms on occasion, so make sure that you can deal with them when we do run into them.